All right, folks. I'm going to be your moderator today for the panel discussion. My name is Rich Brueckner from insideHPC. We're a news publication. That's all we write about is high-performance computing. But I think this is my third year helping Dell out. They were kind enough to ask me to come back and moderate this panel because it's a topic that's, very centric to what I do, which is write about this stuff. It's the convergence of HPC, cloud, and big data. So what we're going to do here, folks, is we're going to have each of our panelists come up and present first and kind of give you a 5-10 minute overview about what they're doing with this convergence. And then we'll have have them come sit up here and take your questions. And I really encourage you to ask questions and make this an interactive thing. We don't want to make it scripted. So why don't we start with Andrew Rutherford from Microsoft, our first panelist, and we'll get his slides up here. And yeah, great.
How's everyone doing this afternoon? Everybody hear me okay on this mic? So my name is Andrew Rutherford. I'm here with Microsoft on behalf of Microsoft and Dell. Wanted to talk a little bit today about the engineered solutions that Microsoft and Dell have been working on together over the past about year and a half, from our original launch to the most recent announcement at Dell World this year. So one of the biggest focuses kind of just across the industry that Microsoft has continued to work diligently to address is how to better integrate cloud solutions with an on-premise solution, right? So we know that the industry is moving that direction. We know that it's not going to stop moving that direction, but we also know there's a whole lot of gaps there, right? So what we're going to chat a bit about today is going to be the CPS solution that we co-engineered with Dell using all Dell hardware, Dell as the preferred OEM vendor, and integrated all of the systems that Microsoft is able to bring to the table. Since the release of Windows 2012, System Center 2012, and the ongoing integrations with Azure, we've been able to basically kind of build this as a do-it-yourself platform, right, across just about any OEM vendor, and it was kind of pieced together, and there were a lot of gaps in the industry, gaps in what end user, IT managers, IT directors were able to do from a knowledge-based standpoint, right? Well, what if we were able to alleviate all of that? What if we were able to approach any industry, any environment, any IT issues with just a one-stop shop, turnkey solution? So that's what we partnered with Dell to put together. So the cloud platform system, we have standard and premium editions. For today's purposes, we're just going to touch on the standard edition to talk about kind of the scale out and rollout models there. The analytics platform system is available as well. It is a much larger solution focused around HPC analytic compute and integrations with SQL as well. After this, if you do have any questions specifically around either of those, feel free to come find me on that. Sure, is that a little better? There we go. So looking at just the challenges of reviewing IT infrastructure, right? Traditionally with IT infrastructure, you have a sprawl of equipment, right? It's continuous sprawl. It's something that's tough to really get away from because it's been the industry norm, right? From a cost-effective outtake at it, as well as just getting into the cloud itself, right? There's a lot of gaps as far as how do I integrate in the cloud. Do I want to lose all control of my data? Can I get to it at any time, data anywhere, anytime, right? That's always a huge concern from any IT environment. So looking at just kind of the top 5 categorized issues with moving into the cloud, right? Expertise, complexity, scale, time, and cost, right? You're going to look at that from any organization from the top down. Well, what if there was a way that we could wrap all of that up together in a simplified solution with a single OEM vendor as a turnkey solution, have it delivered at your door, pre-configured, all ready to go? We were able to do that, right? Some common customer requests. I want my cloud and I want it now, right? We need an easy to manage and scalable solution to run our Windows and Linux workloads. It's a cloud. It should always be available all the time, right? From a support standpoint, that's always a huge issue, right? Support, having a multi-vendor solution, looking around to try and figure out the he said, she said game between the vendors. Where do I go? Who do I get help from? We were able to alleviate every one of those concerns with our CPS solutions. There we go. So I mentioned, we've always had the kind of do-it-yourself model, right? You could take any piece of hardware for the most part. You could apply a Windows platform to it. You could build out a Hyper-V solution. You could use different components of System Center, whether it be VMM, SCCM, SCOM, whatever the case is, build it out, and then use Azure services in any way, shape, or form that you may want to use them, right? And just use it as gap fills. Well, we took that to another level. We came out with the CPS standard system and the CPS premium system. CPS standard was kind of our next level system that we launched to appease the masses from an SMB to mid-market space. The premium solution is going to address any of your larger corporations, global-sized corporations as well. From a scalability standpoint, this is where we really wanted to kind of integrate into the market. When you talk about scalability within an IT infrastructure, we want to build it around Dell's model, equipment model, of grow as you go, right? You don't need to just put an oversized solution in there and then hopefully grow into it, overpay it, and really kind of do the guesswork there. As you continue to grow, we want to be able to have a solution in-house from a software-defined perspective that can just complement directly with a specific OEM vendor. In this case, it's Dell, right? They are a proprietary vendor on this solution. So when we look at it, from an Azure perspective, right, when we go from the cloud back down, right, we want it to be a consistent platform, right? No longer do we want the days to be there where you've got multiple UIs running, multiple systems to log into, having to worry about different components of any kind of IT infrastructure, learning new UIs, new feature sets, et cetera, right? So with Azure, with being an Azure consistent cloud and a box solution, essentially, we built this based on a proven technology, right? Azure's been around a while. We've always had the plugins for Azure to integrate with any IT environment. We now just have it rack stacked and ready to go, delivered at your front door. From a software-defined data center technologies position, right? Azure services will basically redefine the economics of any IT infrastructure from a cost initiative standpoint, from a scalability standpoint, and from a support standpoint. Speaking about the support, you do have a single point of support at this point. Dell will be your single point of support. Microsoft has partnered with Dell to make sure that all of those resources are readily available to you, the end user, and you've got a one-stop shop at that point. So, going back to just our general premise here, we want to just spend smarter, simplify everything, and scale faster, right? So, the accelerated time to value, lower infrastructure costs, decreased risk and complexity. Based on a 1,000-user organization, this was the cost breakdown that we put together from business productivity, risk mitigation, IT productivity, and IT infrastructure cost reduction. All key things that anybody from a CFO, CIO level are going to want to look at. Aside from just the compute standpoint and the scalability and what it's going to do for the infrastructure, when you equate any kind of dollar amount to it, it starts to speak volumes real quick. Simplifying everything. We've got security built in by design, automated update management experience, optimized for Microsoft workloads, single point of contact for support. Again, I cannot stress that enough when you talk about moving to a solution that moves into the cloud and having that many moving parts, and faster problem-solving resolution through the standardization, right? So in looking at this, again, going back to just the simplicity of the solution, the business continuity through integration with Azure services for disaster recovery and backup, it removes a lot of the key difficulties that IT professionals are going to have there, right? And it removes, not only from a hardware standpoint, but also from a multi-vendor standpoint, takes care of and addresses just about any need across the board from a networking perspective, an on-prem solution, an off-prem solution. And the great part about this solution is you're able to build out a hybrid solution where you can actually have the two interact with each other from the public cloud back to the on-prem solution seamlessly and in an automated fashion through System Center. So I mentioned the integrated management services, right? From configuring and deployment, service administration, backup, disaster recovery, any kind of monitoring for not only Microsoft-led softwares, but any third-party software as well. Any monitoring can be done, any updates can be done as well through the automation tools within System Center. And then any patching and update, also another automated process, right? Especially when we talk about smaller IT shops or getting your IT staff to work for the business and not work to keep the business up and running. System Center from just a single pane of glass platform can handle not only a Microsoft workload, but also a heterogeneous environment if you are running Microsoft Linux and even VMware within this stack. So the scale, right? Powered alive in 3 hours or less. You can start very small with this, right? You could build this for a test dev environment and slowly migrate into it, right? Start with 3 or 4 nodes, scale up to 16, and then start to put those nodes together and work together in a converged environment, right? What if we were able to deliver a predictable performance through the end-to-end solution, right? We're able to do that with a CPS solution and the Microsoft software stack tacked on top of it. So, again, talking about the modular design, we're able to scale any on-premise environment to a brand new level. We're able to scale any cloud solution to a new level, and we're able to give you the integration to do a hybrid solution there by incorporating Azure System Center, the Hyper-V platform, and then Dell is our preferred OEM vendor with a CPS solution. So with that being said, the next few slides, I'll kind of hand it back over to Rich here. The next few slides are really just more about speeds and feeds, which if you have any questions about those, feel free to roll them to me in the panel discussion.
Okay, hey, thanks, Andrew. Well, our next speaker is going to be Dr. Craig Stewart from Indiana University, and we'll get his slides queued up. He's got a microphone.
Okay, does anybody know what it means when a tenured faculty member takes off their watch and puts it on a podium? It means absolutely nothing, but I'm not a tenured faculty member. My name is Craig Stewart. I'm the executive director of the Indiana University Pervasive Technology Institute. I'm the principal investigator for the Jetstream project, led by Indiana University. If you have not stopped by the School of Informatics and Computing booth and picked up one of these, get one. All the cool kids are wearing them. And our major partner in the Jetstream project is the Texas Advanced Computing Center. So I'm wearing a TACC lanyard. And Dell is our vendor for this system. And I want to sort of pop up a little and be a little bit more general. And just, let's take a look at where we are right now. More diversity, more uncertainty in processor roadmaps than there has been in a long, long time. It really isn't clear what the vendor roadmaps are going to get us in terms of processors that work in 3 to 5 years. Real uncertainty there. More demand for a greater variety of computational resources than I think we've seen in a long, long time. MapReduce workloads, big databases, low latency MPI applications, fine threaded applications, high throughput applications, just tremendous diversity in what any organization can see in terms of needs of their researchers. You've got to deliver a lot of diversity. You're worried about being captured by any particular vendor. 20 years ago, Indiana University had a very simple strategy. We thought there were 3 HPC architectures in the world that mattered. We tried to have one system of each of the 3. You cannot, at any reasonable size university, have one reasonable size representative of every major hardware architecture out there today. So what are you going to do? And our answer is that we will invest and run locally, and we will run nationally as well. So what is Jetstream? First of all, Jetstream is a first-of-a-kind cloud system funded by the National Science Foundation. The NSF has funded multiple experimental grid and cloud systems before. So if you are a computer scientist and your research is building cloud systems or building grid systems, the NSF has funded systems for that. If you are a scientist and you want to do your research on a production quality cloud system, there has never before been a system that the NSF delivers that does that. It is designed for interactive work. It is designed very much for people working in the long tail of science. If what you want is 5,000 processors next week, the NSF-funded cyber infrastructure has delivered that for a long time. If what you want is a handful of cores now, whenever now is, that's just something the NSF hasn't done. So Jetstream is designed to be interactive, it's designed to be cloud-based, it is designed to be user-friendly, and it is designed to make NSF cyber infrastructure more valuable to a larger community. In the atmosphere, the Jetstream is at the border of 2 large bodies of air. In the cyber infrastructure environment of the U.S., Jetstream lies at the boundary of the existing NSF-funded cyber infrastructure and users who will be new to that cyber infrastructure. So we intend to bring thousands and thousands of users into the NSF-funded cyber infrastructure over time. Jetstream will enable users to run virtual machines, and I've got a screenshot here in just a second. Move your data around with Globus Transfer. We have a special module that is designed to allow students and researchers at universities with very, very poor local cyber infrastructure or local networking to run Jetstream through virtual desktops, and publish VMs with the DOI. So one of the tremendous problems in research today is making computational research, or frankly any kind of research, reproducible. So one of the things that we will allow people to do is run an analysis in a cloud environment, take their VM, their data, their scripts, their output, roll it up in a tarball, publish it with the DOI, so that when you go to submit your scientific research to a publication, you can have a reference to the VM with the data, with the scripts, with the output that you use to do your research. The Jetstream system is going to run like a real cloud. Half of the production hardware will be in Bloomington, Indiana. Half of the production hardware will be in Austin, Texas. If you have not already gone out to visit TACC, I recommend that you do. If you go to visit TACC, you will be able to see Jetstream. I don't think they'll let you touch it, but you'll be able to see the Texas part of Jetstream. We have a small test system that's going to sit in Arizona as well. The Jetstream system is going to be very standard cloud in terms of most of its software, CentOS, OpenStack, KVM, and then on top of that will be the University of Arizona Atmosphere interface. OpenStack comes out with a new version every 6 months. We have to have a test system to test on. So this is it. This is the Atmosphere interface. The key part of Jetstream is to pre-bundle VMs that do scientific analyses that people want done so that you can just click on an image and run it. So for example, if you want to do Bayesian phylogenetic analysis, some people do, I believe it's legal in the state of Texas to do that, then you can just click on a VM that says Mr. Bayes, which is the most popular Bayesian phylogenetic analysis tool out there. Jetstream and the Atmosphere interface will build you your own VM, which you can then work in as if it was a local machine, and it has all the stuff in it that you need to properly run Mr. Bayes. And this is really the critical thing about Jetstream, is that we are pre-packaging VMs to meet scientific researcher needs. So as easy as other cloud systems are, Jetstream is designed to be even easier by virtue of having these pre-built VMs. This is a picture of it. Since you can't touch the part that's in Indiana, this is a picture of the part in Indiana. Status highlight. So it's it's here. It's running. The NSF has accepted the test gear. We are running live demos on the test gear now. We had people who really know what they're doing live demos yesterday. Today I did a live demo. So yesterday's demos were introduced with so easy even a caveman can do it. The question is fine, can the PI do it? And the answer is yes. It's running. It will go live in early operations mode on the 20th of January. And if you go to this URL right here, www.exceed.org/allocations, you can request a startup account on Jetstream that you should be able to begin using on the 20th of January. And a few closing thoughts. In terms of scientific research, the open research community, there is not enough money in the system to satisfy everybody's needs. That's all there is to it. The only way for us to survive is by providing local resources and using national resources, meet the tremendous diversity of the tremendous amount of researchers we see out there. And in terms of cloud, big data, and HPC, I think we also need to recognize where there are commonalities. Node level performance. Everybody benefits from improvements in node level performance. And recognize where there are differences take advantage of the opportunities for leveraging technology that has multiple applications, but also recognize that you can't build one machine to solve all problems, and it will take a diversity of machines locally and nationally to meet the needs of the researchers at any particular university. And with that, I do want to thank Dell very much. They have been great partners on this system, and thank all of our other collaborators. The thing about the JetStream team that has been so wonderful is that we are including a large number of domain scientists. So we have astronomers, biologists, earth scientists, social scientists, and we are counting on leaders in scientific groups to serve as pathfinders within their communities of practice and help spread adoption of JetStream. And with that, I think I'm in good time.
Yeah, very good. Thank you, thank you. Our next speaker is Niall Gaffney from TACC. We'll get his slides up, give him a mic and the clicker.
Right. Thank you. Well,
you'll need the clicker.
I'll need the clicker. I can't.
Craig,
yes.
Gotcha.
Well, I could just point at Craig. I mean, we work together in the cloud now, apparently. All right, so I'm Niall Gaffney. I'm Director for Data Intensive Computing at TACC, and I'm here to talk about sort of one system in particular, but a lot of what we're doing here is this real intersection between cloud, HPC, and big data. So if I can figure out the clicker, here we go. So long ago, cluster computing all started pretty much the same. We had, clusters such as, the Grendel cluster here, which is a classic Beowulf cluster, the original Google server, were just commodity hardware that were put together and then, used to attack problems of the day. But as we grew these out, the two systems diverged. We really have Stampede up here, which is a classic HPC system where we have MPI jobs running where we're trying to take advantage of low network latency. And here's sort of a Google system down below where we're running large MapReduce type jobs. And in those sort of systems, you're moving the code around to benefit from the fact that you can have better access to the data to get rid of the latency there. It's sort of divided the way that we work. And working at TACC, we have many people who try and come onto something like Stampede and do things that they shouldn't. And in particular, in 2011, one that sort of came out was that people came to run Hadoop on an HPC system. And they would do this not really considering what they were doing. It seemed like a big system to them. But what they were doing is they were coming to a system that was specifically designed to have, low latency message passing and have a big shared file system optimized for large sequential reads and writes. And then they'd come to it and they'd run something that's doing exactly the opposite. And our sysadmins would see this and they'd sort of swat them and say, go off and use a real Hadoop cluster. We actually deployed a Hadoop cluster at TACC to handle people who needed to do these workloads and get them off of Stampede where they were impacting people. But after that, it really became clear to us that it wasn't just big data problems that we're having problems with. Stampede itself, great system, supports thousands of users every year, more than 2,000 projects. And we have, half of the users are running sort of well-tuned commodity codes, your AMDs, Ambers and NAMDs of the world. And they're really doing well on the system. But we've got another 50% of users who are just running, well, pretty much anything out there, ranging from, R scripts to some actually very well-designed personal codes. But there are many that sort of can't take advantage of Stampede because of the limitations, because it is specifically designed one of these models in mind. And it's not isolated just to data people doing what they might consider the wrong thing on the system. There are a lot of people who can't do this in a high performance realm simply because of the way the system works. So for this, we built a system called Wrangler that's also co-hosted at Indiana. It was a system that was designed mostly with sort of big data needs, but coming at it from an HPC point of view. It's a Dell system that we've deployed at both sites that has a subcomponent built by a company called DSSD, which eerily is it's our flash component and has absolutely no SSDs in it. So it's probably the worst name you could pick for a company is DSSD, but they're a fantastic company in building our flash storage system. We have about 600 terabytes of distributed shared NAND flash storage that can be used across all of the 100 compute nodes at TACC. And that's not having just individual SSDs and nodes. That means that all of the nodes can actually go and see all of the flash memory. And this suddenly changes everything for you. Suddenly your latency problems go away. You can get to data very quickly. You can message pass very quickly, all in the same environment. Having something like this is really allowing us to sort of pull together this notion of it's no longer about having the right big data system, and it's no longer about having the right HPC system. It's actually about having both of them all together, being filled in and bridged by this NAND flash storage. And working with many people here on this system, it's working with data people who, again, aren't necessarily HPC people. And a lot of what we've been doing in the system, just as sort of to bring in the cloud portion of it, is allowing people to provision the system in different ways. So we are doing more dynamic provisioning of the system, whether it be for Hadoop or for MPI type jobs, or actually for custom workflows that we would support sort of in a cloud-like push and click as a service environment. What have we been doing on this? Well, we've been doing many different projects over the past 6 months that we've been in early operations. One in particular that was sort of a real eye-opener for us is this all-to-all genome sequencing comparison, where they're looking at similarities and differences in behavioral characteristics of certain animals and how those may have come to be. If you will, it's comparing 4 letters of the alphabet over and over and coming up with how things evolved into other things. It's a highly throughput demanding problem requiring small I/O, and in fact is being done in a SQL database in this particular case. We tried for many years to run this at TACC and couldn't. It would fall over, there would be a network problem or a disk problem or something along the way. On Wrangler, we were able to solve their problem in less than 4 hours, and that's just by having this high transaction rate flash storage. But we're also able to take simulated data. Mike Norman from San Diego Supercomputer has been bringing a lot of his simulation work and doing feature detection in it, and sort of taking high performance results and using data analytics techniques to get the final answers. And lastly, we've actually been doing some out-of-core computations where we've been seeing an improvement of factor of 5 over what we can get out of Stampede on HPC code. But then if you take the same code and run it completely in-core, it's only a factor of 2 faster by running it in full DRAM as opposed to running it with this flash memory here. So as we move forward to exascale, we really think that this is one of these components that's coming. This is where a lot of these things are going. It's making things complex, as Craig was saying, but this is where the world is coming together, and this is the convergence that I see. So it's things like this flash storage, the distributed flash storage, that's going to get us there. And it's also optimizing of services for people and allowing people to select things, much like what they're doing in Atmosphere, to take advantage of the right hardware and the right systems to move forward. And this is really where we're going. I don't know if people are going to be doing sort of NAMD type computations in Spark, but I think Spark will be used to analyze NAMD computations on systems in the near future. And so with that, I'll turn it over to the next.
Thank you, Niall. Thank you. All right, we got another speaker. Wojtek is going to swap laptops. And just give us a second here, but after he's done, we're going to do a little panel, and we're going to encourage you guys to ask questions. And this will be, of course, on the convergence of HPC, big data, and cloud. And Wojtek is from Monash University. You all set?
Getting there. Yeah,
oh,
thank you very much. So I'm Wojtek Goscinski. I'm from the Monash Research Centre. That's in Australia, Melbourne, if you're not sure. The best way to describe what we do is to actually show you a little bit of the scientific output. This is a protein called porphyrin. It's a protein, the structure was identified at Monash University in James Wistock's group, and it forms a pore. It's a pore-forming protein, right? It forms these sort of shapes. It's a fairly simple animation, obviously, of what this protein does. And in a second, you're going to see how it unfolds. The significance of this protein is that it's actually a protein that kills things in the body. And it actually goes out and kills cells. It's part of the way the human body kills cells, right? And that's a necessary process, biological process. Here it is unfolding. That pokes a hole in the cell. That lets all sorts of other things get in that cell, and the cell dies, right? It's very significant. So if you actually have a look at the paper for this, the publication, right, that describes this structure, you get paragraphs and paragraphs of text like this. And it is basically effectively, here's where we got the data, here's what we did with it, then we did this, then we did this, then we did this. The research group involved have developed this really amazing ability to know how to process all of these different data sets and put them all together and gain a single picture of what all of these data actually mean. Right? And it's very sophisticated. They've, over time, built these workflows to do their data processing. And this is where the knowledge really is in that research group. What's also significant is that they're doing really fundamentally... There we go. They're doing data capture from a number of sources. They're using molecular crystallography, they're using negative staining, they're using cryo-EM. These are all data sources that they're using, and each data source gives them a little clue basically about that structure. They're doing a lot of data integration and data processing. They're bringing all of this together, and as I said, every single bit of data gives them another little piece of information about this protein. And they're also doing modeling and simulation to then get another picture from the other side of their protein as it's modeled. And you saw that outcome in the video. So the Monash Research Fabric is what they're using to do this work. And it's fundamentally a software-defined hardware environment, and that's the direction that we're moving entirely. So we run a dedicated research network. We're moving to a software-defined research network, a research cloud of about 10,000 cores, and that supports largely most of our compute. So actually all of our high-performance computing is done over the top of that cloud environment. And Ceph and Lustre file systems, and we're very strongly moving to a Ceph architecture because, again, it gives us the flexibility to be software-defined. So we support a number of clusters over the top of that cloud environment. We support VMs in the same way that was just presented before with Jetstream as playpens for researchers. We also support dedicated virtual laboratories, which are really sort of coordinated environments. Instead of just providing a free-for-all VM for researchers, we provide these coordinated environments with specific tools. And an example of that is a environment specifically for structural biologists, with specifically all of the tools that structural biologists might need to do their research. And finally, we support a lot of remote desktop work. The same sort of case that was presented for Jetstream, we're supporting communities that don't have background in big data problems. And so we're basically we're supporting communities who have desktop tools and have used those desktop tools fine up until now, but now are capturing so much data that they can't process it any longer. And so what they're doing is coming to us with those problems, and effectively our only solution is to give them a desktop environment to help them. But that allows them to scale up over time and start using the capabilities of the underpinning cluster or the underpinning high-performance computer. So scientific desktops, specifically for particular communities, are really, really something that we've been doing a lot of, and we've been investing a lot of time and energy into building community-driven environments, as we saw with the Jetstream system as well. And this is what our usage is like. These are environments that are used on a day-to-day basis by many research groups. They're integrated into their research workflow, and people come in, researchers come in the morning, they bring up a virtual machine, and they use it as their desktop environment really for the rest of the day. So on average, we have about 50 users per day of these environments, and about 300 to 400 users across Australia. The other way to look at this is that we believe that we're actually building the 21st century microscope when we do this, because the data source really now it offers such a very, very specific bit of information about something like a biological structure. You need to integrate a whole lot of different data sources, and the computational environment and the whole fabric that you use to do that is becoming more and more important over time. The ability to bring together all these clues and perform a range of different types of processing and simulation and so forth. So let me just finish with another example. This is a gentleman called Andreas Fouras, who studies, well, he's an imaging scientist actually, but he does a lot of lung imaging work. He uses a synchrotron to do that. And our environment is used to help him do that in a real-time manner. So literally, as he's doing his experiment, he will bring up a cluster. We provide him the tools to bring up a dedicated cluster, really on demand. It's built for him in about 15 minutes. And he then uses that to do near real-time processing of his data, CT reconstruction specifically of large-scale imaging data as the experiment is going on. The intent here is that he can modify his experiment with the data information that he's gathering. With all of the information that he's gathering from the analysis, he can actually modify his experiment and get better results. And this is the data. This is the output. So this is a set of lungs. This is real 4D data. You'll see it move in just 1 second, I hope. Or not. No, I'm not. Sorry. It's not playing, but I can assure you it's very, very beautiful data. It does move, and you can see real rabbit lungs as they're actually breathing. Perhaps I'll just come over there and see whether we can click the button and it'll play. Whoa. No, doesn't look like it. I apologize for that. Thank you. Oh, there we go. There we go. So that's full 4D data of actual rabbit lungs. It is imaging data. It's not simulated, and it's a very, very difficult experiment to perform because you need to do CT reconstruction while an animal is actually breathing, and that's why you need that real-time feedback and be able to see your results as you're doing your experiment.
Thanks, Wojtek. Great. If we could have our panelists come up and take a seat. We're going to encourage the audience to ask questions. I've got a bunch, but I'm going to start with the audience. You guys are going to share a microphone. And I would... Yeah, oh, you got it. Okay. We got two of them. I didn't know that. Is that one on? Say hello?
Yep.
Oh, great. Excellent. Hello. Okay, guys. And when you use that microphone, it's hard to hear out in the back. You're going to have to be right up here. So... Well, again, in case you joined us late, I'm Rich Brueckner from insideHPC, and the theme of all this was the convergence of HPC, big data, and cloud. And do we have a question from the audience before I start? Question? Okay. I want to ask you about security, okay? And Andrew, I know in your business, I mean, people are saying that the cloud is more secure than almost anything you could build in-house. Would you agree with that? And then I want to hear from the other guys on how important security is and what the challenges are there.
So yes and no.
Yeah.
When we look at it from a Microsoft perspective, I would say absolutely yes. And the reason being is because, at least the biggest reason in my mind is because you're not giving away any piece of your business to a public single entity cloud provider. You're keeping it all in-house. You're keeping all the management of not only the public cloud, but the on-prem private cloud, and then the ability to actually tier out any of the data usage in any scenario in a hybrid cloud model, all within the Microsoft stack. So from that standpoint, I would have to agree that, yeah, from a cloud perspective and cloud conversation, it is probably the most secure way to go about either handling your data, keeping it to yourself, or just analyzing it overall.
Yeah. Well, Craig, I can just imagine, he's got these professors, right, and they want to be root and everything. What are your challenges there?
Well, being rude is overestimated. So first of all, at a very fundamental level, there is no evidence, as far as I'm concerned, that anybody can actually run a system that will survive a concerted attack from the best hackers in the world. I mean, I think we've just seen that over and over and over again. With multiple universities in the U.S. being offline for extended periods of time. I mean, security is a real headache. There are certain security advantages to being in the cloud in some ways, particularly if you are able to manage legal arrangements as well as data movement. There are certain advantages to having your data on site and having it protected by your own network people and your own network monitoring. Our approach in Indiana is to keep data that are sensitive, protected health information. Those sort of data we keep locally inside our firewall, encrypted as much as we can, and then beyond that, it's very much a fine-grained problem where you have to look at every data set, how easy is it to get identifiable data out of it, and what a headache is it. And it's, the answer on average is that every problem is worse than every other problem.
Okay. Niall? Oh, yeah. Okay. You got it, Mike.
I could go with, yeah.
Yeah.
So I think I'll sort of extend on what Craig was talking about. At TACC, we've been working very closely with a lot of the health systems here in Texas, the MD Andersons, UT Southwesterns of the world, and the coming Dell Medical School. And so we have quite an eye towards sensitive data. And I think it's more than what most people think about, especially when you're dealing with the professors of the world who are coming in and their goal is to do research. They don't think about leaking data accidentally. They don't think about what the environment could be, how it could be compromised, even accidentally. So we are working very closely to create environments that protect people from themselves. So that only the data is exposed to the people that it's supposed to be, right. and they don't have a home directory where they could accidentally put things, and then a graduate student copies it to his laptop, and the lawyers descend. So there's a lot of different parts at play here. I mean, the security components, I think, of the hardware, the encryption, all of those things, there are many lawyers behind those right now, making us do the best we can. But it's those other challenges, I think the human element, and especially in research, the Dottie professor element, that comes to play.
Okay, yeah. Wojtek.
Yeah, I think we approach this in a quite a pragmatic sense. So we believe that we're developing playpens that allow researchers to do their work, and that means fundamentally that we have to accept an element of risk with a lot of the systems that we run. We just fundamentally do. On the other hand, we also run a lot of medical informatics type work. And we have ISO 27000 accreditation to do those sort of things. That does impose a very high cost, and it's a completely different, largely a completely different environment. It's a far more controlled environment. But having said that, we are trying to work out mechanisms, in a sense, to still provide as much flexibility in those sort of environments, whilst ensuring that we tick all the right boxes. Look, none of this is easy, and we have many conversations with the security parts of the organisation, with networks in particular, which are a lot of the time negotiations. And in a sense, we as a research centre will be the ones going into bat for actually opening things up more and providing more flexibility rather than less. Yeah.
And I had a particular question for any of you panelists that are using Hadoop, because this was not designed for security, and is that presenting special challenges in that area? Any of you guys have a... Well, okay.
It's a different challenge, I think, in the Hadoop environment, because most people who have PHI data don't know how to spell Hadoop. And so, at least in the research realm, we aren't having as much of a concern with that, because we just need to onboard people at this point.
Yeah.
That said, on Wrangler, the way that we are handling security is we don't actually have a single Hadoop cluster. We stand up Hadoop clusters for projects on demand. So again, we can lock things down. It is just that researcher who has access to the data in that system while they're doing their Spark or MapReduce.
Okay.
And then once they're finished with that, they migrate, we will migrate the data out from there into the sensitive data area, so that, again, we don't have people just accidentally leaving things around.
Yeah. Craig, did you have something to add?
I think Niall got it.
Yeah? Okay, great. Well, my next topic is kind of related. This convergence with big data and HPC is Apache Spark, okay? And from a journalist perspective, I see the hits for anything to do with Spark are just off the charts, because I have another publication called Inside Big Data, and those are the stories that are getting the reads. And I want to see, are you getting that kind of a feel from the world out there that they want to be doing Spark? And it sounds like a great way to get money if there's all those interested people. But any comments on that? Spark? Who's doing Spark? Okay.
Oh, I'll start just by saying that one of the things that's really interesting about the computing environment today is that question is different every 3 months. There's always something new, and there's just a tremendous amount of innovation in terms of computing environments, application environments. So we're interested in supporting Spark. That will be one of the things that we look at very closely and very quickly as soon as Jetstream goes into production. But I think one of the key things is developing environments that are flexible enough to support the next new thing, whatever that is, because it's going to be different in 3 or 6 months than it is today.
Yeah. Go ahead.
So on Wrangler, I mean, Spark is probably got as much buzz around it as what's going on in the blogs around the world. But it's the same problem. It's the adoption of people who are coming from a desktop environment. So we're working very closely with several developers at TACC right now who are porting metagenomic codes into a Spark environment to really accelerate them. I think that's sort of the cloudy side of it, is getting the applications there for people to work with. But the other thing that I'd just like to say about Spark, it really is sort of that first software package that is bridging HPC and big data. It's bringing similar concepts as what you find in your MPIs to bear with data, and so that's where these walls are starting to blur and come down. And I find that, as I mentioned in mine, Spark is not going to be doing a NAMD, but it may be analyzing it very soon hereafter. And so we think that Spark is going to be, along with a lot of the other things coming out of Berkeley, out of that lab, are going to be key components for all sorts of computing over the next 10 years.
Okay, that's exciting. Any other comments about Spark? Okay. All right. Well, I would like to open it up. Does the audience have any questions for our panelists before I go to my next topic? Don't be shy. They came here to answer questions. You've got one. Go ahead.
What technologies are you looking at over the next 2 to 3 years that you think will make your environments more elastic and make your environments more accelerated? What technologies are you considering over the next 3 years?
If I could just jump on that one real quick, because I think it's the two of us can both talk to it, but it's the convergence of the two systems we've been talking about. Having a cloud-type environment standing near or around HPC and big data systems is going to give us that flexibility and yet still allow us to have that bare metal provision power to move things forward. So I'm really excited to see what happens when we have a distributed cloud environment and with Wrangler, both between the same data centers. What can we enable in much more of a as a service type environment that we couldn't before? And so,
yeah, just to touch on that point, from a Microsoft perspective, the biggest accelerator that you're going to see from our end is going to be the continued focus around engineered solutions and converged data centers. Primarily speaking to the 2016 platform that'll launch next year on Microsoft's usual 3 to 4 year roadmap. Without getting into any real specifics of it, what you'll see around that is a collaboration of all of our tools take the next step at the exact same time versus it being pieced together from back to the 2008 platform that we kind of came out and said, hey, here we are. 2012 R2 really came out and said, hey, here we are and we can do it now. And with the 2016 platform that'll be out from Azure to System Center to our just Hyper-V and Windows platform, the capabilities that will be included that you will see there are going to be able to take software-defined data centers to that next level just inherently within an OS platform and be able to replicate that to just an all-encompassing cloud solution.
Okay. Great. Any other questions from the audience? All right. So I have one. To Craig's point, I think the buzz 3 months ago was Docker. And I might have missed it if any of you mentioned Docker, but are any of you using it? Do you think is the future bright there for this area? What do you think?
The future's bright.
Yeah?
the current status of Jetstream is that it exists, it's sort of running, it's been stood up. It has not yet officially been accepted by the National Science Foundation. My life consists of two pieces. The things that I need to do between now and the day we have our acceptance review and the NSF actually gives us the money to run the system, and things that I think about the day after that happens. Docker is one of the first things that we're going to pay intense attention to right after we get through acceptance. We've already got people that are building applications running Docker. So we had a graduate student from SUNY Binghamton in our booth yesterday demonstrating things that he had built with Docker. And it's exciting technology, and I think there are real opportunities to build flexibility in applications using Docker that would otherwise not exist. So I'm excited about Docker a lot.
Great. Anyone else have? Yeah? Wojtek?
Yeah, so we support a lot of environments because we are moving to a fundamentally a software-defined everything model where we bring up dynamic environments for very specific purposes. Docker does provide us that ability to be able to support software across all of these environments a lot more easily, right? And we're very, very keen on using it more as time goes on.
Okay, great. Any questions from the audience? Please, don't hold back. Okay. One last question, guys. Actually, our next talk is going to be about the National Supercomputing Initiative, the NSCI, from Obama's executive order. And when I looked at the agenda for this convergence of HPC, big data, and cloud, it was all in there. And you have any comments about it? I mean, it seems to me very encouraging what's going on there.
Well, so I think it is very encouraging, first off. There are a number of problems in common across any type of application, any type of architecture. I mentioned node level performance. Better node level performance will have to get attention as part of NSCI, and that will benefit everybody tremendously. I think that, given the amount of money that's going to be available, and the amount of money that any part of the NSCI is going to take, we're going to have to look for as many investment opportunities as possible to make sure that everybody benefits as much as possible from the overlaps in the needs and the technology developments.
So I wanted to just say exactly, it was sort of the point that of what my read on NSCI is, and Dan will come in a little bit and talk to folks about his take from that. But it really is, I mean, the complexity of these systems to make something go at exascale is growing, and I wouldn't even say it's exponential. It's astounding what you're going to have to do to be able to get performance out of these systems in the coming 5 to 10 years. And in order for this to work, we have to pool everything. And I think that's really what's at the heart of this is, we can't go it alone. We can't let just, those who are doing sentiment analysis go their way and hope that those who are doing, large protein docking codes can find their way as well. So it really is sort of a raise every boat situation here. And right along with that, I think the hardware is coming to do that, and that's, I think, the other component that, we talk about doing things, but you're starting to see systems like Wrangler, you're starting to see systems like Comet, where we are beginning to blend these things into an environment that's going to lead us to the next scale of computing.
Yeah. Well, thank you, Niall. Any closing thoughts, folks? Because audience, any questions? Okay. Well, I think we're out of time. So let's give our panelists a big hand. I think they did a great job.